Hello and welcome to the course Design Borefields with Confidence. This is the first chapter of the fourth part of this course, and we will be talking about pressure drop today. Now, what is actually the pressure drop? Now, the pressure drop is defined as the difference in pressure in your system between two different points caused by friction. Now, this is friction between the fluid internally, but also the fluid and the pipe wall. And basically, this concept relates also to a certain amount of energy, a certain amount of effort that our pumps need to do in order to pump our fluid through the system. So that's how we should think about the pressure drop. Now, this is influenced by quite a lot of factors. And it depends on the flow rates, the pipe diameter, the viscosity. And you can imagine if you're pumping water or you're pumping honey through a system, well, it takes quite a lot of effort to pump this honey through when you compare it to just pumping water. So viscosity plays a role, the flow rate plays a role, etc. But also your routing of the pipes plays a role. If you go straight to your location where you want to be, or you take 8 bends, well, having more bends will also require more effort, will have a higher pressure drop. The number of interconnections and so forth. So when we're talking about pressure drop, we can classify this in either local losses, minor losses, and on the other hand, we have friction losses, major losses. Now, these local losses are quite straightforward, right? Because you can point at them. These are the bends, the junctions, the control valves on your manifold. These are actual components you can point to, and each of these components has a certain minor loss, a certain local loss, defined by a certain K value. Now, these K values, you can find them in tables. There are some over in the textbook, but also typically your manufacturer or your supplier can give you a certain K value for the components they supply you with. So these are the local losses. Now, on the other hand, just the fact that you have pipes with fluid running through will also give you friction losses. And these typically depend on the length of your pipe, and the longer your pipe, the more friction losses you will have, of course, and also your pipe diameter, as we will see in a second. Now, let us now take a closer look at the physics, look a little bit at formulas to understand both the local losses and the friction losses, and to then bring them together in the total pressure drop, which we can reason about and which we also will be using in the next chapters to see how your hydraulic design should actually be made. Now, this is the formula that governs the local losses. And as you can see, the pressure drop, the delta P, is equal to the sum of all these different K values. And so what you do is you take a certain route, you select a certain hydraulic route, and you simply count all the K values you incur, every bend, every junction, every elbow, and so forth. And you sum this, and that you multiply it by a certain factor, taking into account the density, the velocity squared divided by 2. And this is a little bit the kinematic energy. So these are the local losses. The friction losses are a little bit more complicated, because for that we need something which is called the Darcy-Weisbach equation. It's a very famous equation in fluid dynamics. And this expresses the pressure drop due to friction as a certain Darcy-Weisbach friction factor, which we will cover in the next slide, multiplied by the length of the pipe divided by the diameter, again multiplied by this kinematic energy factor, this density multiplied with the velocity squared divided by 2. Now, in order to understand this equation, really we need to talk about this friction factor. And in order to see what this value is, we have to look at a very famous diagram in the domain of fluid dynamics, which is the Moody diagram. Now, this might seem complicated at first, but let us go through it together. So what we see here is the friction factor in function of our Reynolds number. Now, if you recall, our Reynolds number, it told us something about the flow regime, whether we're laminar or turbulent, and it took into account the flow velocity, the pipe diameter, the viscosity, and the density of fluids. So basically, it summarizes a couple of aspects related to your hydraulic design, both the fluid and the flow rate. Next, what you should know is that this diagram is on a logarithmic scale. So the spacings and between 10 to 20 to 30 to 40, they are not equal, which is also why you can see that the horizontal and the vertical lines, they are not equally spaced, but they are crammed together, let's say. So that's a logarithmic scale. So between every step here, you have an order of magnitude difference. For example, in the Reynolds number, you see 10 to the third, 10 to the fourth, 10 to the fifth. So it's every time a factor of 10 difference. Now the reason we are interested in when we're dealing with geothermal design is basically to the left of this figure, somewhere up to 10,000 as a Reynolds. And what you see that to the left, when we are laminar and we are below this 2300, we see a very neat, beautiful analytical equation, namely 64 divided by the Reynolds number. Meaning that if our Reynolds number increases, our friction factor will go down. And then we see this sudden jump towards the turbulent regime. Now, if you recall, when we introduced the Reynolds number, you have this laminar regime, you have this turbulent regime, and then you have this transient zone in the middle. Now, when it comes down to the hydraulic aspects and the pressure drop, there is no real correlation for that. So here there is a sudden jump. More information is in the textbook if you're interested. But what you can see is we go down in the laminar and then we jump up to our turbulent regime. And here we do not have one single line, but we have actually a variety of lines. And this is because of our pipe roughness. Now, you should know that these Moody diagrams, they are not only used in geothermal engineering, but also for the design of air ducts, sewer systems, drinking water systems, whatever. And depending on the material you use for your piping, whether it be metal or concrete or steel or plastic, like in our case, the surface roughness will change. And depending on the surface roughness, also your friction factor will vary. Now in geothermal applications, typically we're at the lowest line, in theory the smooth line, where we have a very smooth surface. And what you can see there is that once we're in this turbulent range, the more we increase flow rate or we decrease our viscosity, we increase in general our Reynolds number, we will have a lower friction factor. So that's a little bit how you should read this Moody diagram, or at least how you should understand the friction factor. Now, if we combine this local losses and these friction losses together, we have the equation which you can see here. So we have the kinematic energy factor, let's say, and this is multiplied by a sum of the friction factor multiplied by the length divided by the pipe diameter, and our sum of all the local losses. And then you see in the graph below that we have this typical quadratic curve in the flow rate. Now, in order to understand this formula even better, let us take a look at a couple of relationships. What can we learn from them? Now, one thing is that our pressure drop is proportional to the pipe length. So if we double our pipe length, exactly, but more or less our pressure drop will also be double. And then another important aspect we see is that our pressure drop is proportional to the velocity of our fluids, meters per second, squared. Now typically when we're designing systems, we're not talking in terms of fluid velocity. We're talking in terms of flow rate, liters per second, cubic meters per hour, and so forth. And what we know is that our flow velocity is proportional to the flow rate. Because basically we have the pipe diameter, it has a certain cross-sectional area. We have a flow rate, and when we divide the flow rate by the cross-sectional area, we have actually our velocity, flow velocity. So our velocity is proportional to the flow rate, and it's also proportional to 1 over the diameter squared, which is exactly used for this surface area. And once we know these relationships, we know that our pressure drop, as seen in the figure, is proportional to the square of our flow rate, meaning that if we double our flow rate, that our pressure drop will also be double. And another important relationship is that our pressure drop is inversely proportional to the diameter of your pipe to the fifth power, meaning that our pipe diameter, one of the many design choices you as a designer can make, has a very, very important impact on what your pressure drop of the system will be, as well as the pump energy and so forth, as we will discuss later in this part. Now, we understand the pressure drop and how it's calculated. So why do we care? Because as said, the goal of geothermal design is actually to make sure that your temperature stays within certain boundaries, and minimum and maximum fluid temperatures. So why do we care about this pressure drop? And the thing is that when we're designing our system, we need to fill in flow rates, or let GHG will calculate it, but anyhow, we have a certain flow rate to our system. And this flow rate will have a certain pressure drop coming with it. And we need to make sure that our pump can actually deliver this pressure drop, because if it cannot, then we do not know that what we simulated from a thermal point of view can actually be happening in reality, because our pump cannot deliver the flow rate that was used to calculate these thermal aspects. So let us take a look at this graph. It's from a NIBE heat pump, and it's a pump graph of a certain heat pump. So you see all these red lines. It depends on the percentage or the power consumption, let's say, of a circulation pump. And the red line at 100% is what our circulation pump can deliver when it's working at 100% of its rated power. Now imagine you have designed your geothermal system with a flow rate of 0.4 liters per second, and you calculate, well, we have a pressure drop of 35 kPa. You look then at your heat pump and you see, okay, this point, 0.435 kPa, it's underneath this red curve. So basically our circulation pump can deliver our flow rate at this required pressure drop. Now for another case, or another designer can make a geothermal Borefield, which is also thermally outstanding, but with a lower flow rate. We only need 0.35 liters per second, but at a higher pressure drop at 60 kilopascals. And now the problem is that this point on this graph, 0.35, 60, it falls outside of what actually our circulation pump can deliver. So our flow can never be that. Our system can never work in this working point, so our flow rate will be lower, meaning that also your thermal simulation will no longer be correct. And this can sometimes lead to undersizings or systems that do not work as intended. So that's why we care about the pressure drop. Now that we understand that, we understand the pressure drop and we understand why it's important, we are ready for the next chapter, where we will deepen our insights in this concept, take into account variable fluid properties, variable flow rates, and also related to pump power and pump energy.